Good. So, yeah, the talk is sort of roughly divided into 5 parts. I'll start off just by introducing things a little bit. Then I'm going to talk about causal influence versus signaling, the idea being that they're not the same thing and should be distinguished. And then, for reasons that I'll explain in that first part of the talk, I'll focus on unitary transformations in quantum theory. I'll talk about defining causal influence in unitary transformations and some initial results that are going to be used throughout the rest of the talk. From there, we'll move from just sort of single unitary transformations to the idea of a unitary process over multiple time steps. Talk about causal influence there. And then onto the idea of what I call a causally faithful circuit decomposition. And we'll see that when we get to it. And then if there's time, I'm not sure there will be, but we'll see what happens. I'll sort of conclude with some speculative remarks on a more interpretational theme about ideas that we might take from all this. The rest of it, I hope, is technically interesting and useful and so forth, regardless of what we think of those remarks. Okay, yes, everything I say is for finite dimensional systems throughout. Okay, so I'm not going to give a very long introduction here. In fact, I'm just going to throw something at you already, which is the idea of a classical causal model. A classical causal model is a directed acyclic graph with random variables on the nodes. There's a little example of one there with 4 nodes, x1, x2, x3, x4. Those are all random variables. And in addition to that graph, the model specifies a set of conditional probabilities for each I, P of xi, given the parents of I, where the parents of xi in the graph are the nodes xk, such that there's an arrow from xk to xi. And then we form a joint distribution over those variables just by taking the product of all those conditional probabilities. And the idea here is that the arrows in the graph represent the relation of direct causal influence. So here we see that x1 is a direct cause of x3, but x1 is not a direct cause of x4, otherwise there'd be an arrow from x1 to x4. It is an indirect cause of x4 in this example, because it can have causal influence on x4 through x3, but that influence is mediated by x3. Okay, now there is by now a large literature on classical causal models with increasing interest from various different communities, for example, people in machine learning and AI, and an increasingly broad array of applications, whether it be automated medical diagnosis or whatever. But they also raise or cast new light on foundational questions, such as this list here that I featured in my abstract. If A is a cause of B, then what sort of thing are A and B? What does it mean to say that A is a direct cause of B? Say we've drawn an arrow in some DAG. I said if there's an arrow from A to B, then A is a direct cause, but what does that actually mean? Do causal concepts involve in an essential way interventions by agents? Are causal relations directed in time? And what in the overall picture is ontic, i.e. factual and independent of the agent, and what is epistemic, i.e. relative to an agent's knowledge or beliefs? Okay, so I'm going to give an account of causal influence in quantum theory, which supplies its own answer to all or most of those questions. But I want to begin, as I was saying, by distinguishing causal influence from signaling. So this first part of the talk is sort of a broadside against anyone who thinks that causal influence should be defined by signaling. And there's certainly quite a lot of literature in quantum information theory exploring general quantum channels, let's say CP maps, and talking about whether inputs can signal to outputs and that sort of thing. And the point I want to make here is that that's not quite the same thing as exploring causal influence. So I'm going to make this point in a couple of ways. Let's consider a classical channel, S. S is just a stochastic map, and it has an input variable X and output variables Y and Z. Well, we can discuss, of course, whether X signals to Y or whether it signals to Z through S. But just a couple of things to note. First of all, it can happen in this channel that X does not signal to Y, and it does not signal to Z either, but it does signal to the pair YZ. So it's easy to think of an example like that. Maybe they're all classical bits, and maybe Y and Z are locally random, but the value of X is written into their parity, something like that. And just another thing to note here, that there's no reason at all, if we haven't said anything about what S is, to assert that Y and Z are conditionally independent given X, which is something that would follow if we were doing classical causal modeling and we drew a little picture with an arrow from X to Y and an arrow from X to Z. In that particular causal model, we would have that Y and Z were independent given X. But here, of course, if S can be any channel, then S itself can set up correlations between Y and Z that are not screened off by X. And so what I take away from this is that if we only talk about signaling through channels, first of all, it's complicated because we have to consider arbitrary subsets of outputs to get the full picture. We can't just talk about signaling from individual inputs to individual outputs. And second of all, we miss Reichenbach's principle, which is that statement that Y and Z are conditionally independent given X, at least when X is a complete common cause of Y and Z. Okay, and here's a second consideration that's part of this overall business of distinguishing causal influence and signaling. Consider this channel here. This one's actually a function, so it's a deterministic channel. Suppose that X, lambda, and Z are all classical bits. And suppose that the output Z is just the parity of X and lambda. Okay, a simple function. But now suppose that actually lambda is hidden from the point of view of some agent. So that agent doesn't know its value, and suppose that they actually just assign probability a half each for lambda to be 0 or 1. Well, then in the marginal channel from X to Z, the output Z is just random, independent of X. From that agent's point of view, Z just has half-half probability to be 0 or 1, no matter what the value of X is. So from the point of view of this agent who doesn't know lambda, there's no signaling from X to Z. But we should certainly say that independently of any agent, there is causal influence from X to Z. After all, Z is the parity of X and lambda. Z certainly depends on X in this functional evolution. So we ought to say that there's causal influence from X to Z, even though there's no signaling from the point of view of a particular agent. Now, of course, the signaling only disappears for a particular choice of the distribution on lambda. It's only for that half-half distribution I chose that the signaling will disappear. So it's a very specific distribution where one finds this. And in general, in the classical literature on causal modeling, this sort of thing is called fine-tuning. We can describe a similar example in the quantum case. Here we have qubits, A, lambda, B, and C, and a C0 gate. And B in that diagram is just being traced at the end. We're ignoring it. So suppose I toss a coin and prepare pure state 0 on heads for the system lambda, and pure state 1 on tails. Well, to an agent unaware of the coin toss, they'll assign a maximally mixed state to lambda ion 2. And from that agent's perspective, there's no signaling from A to C. And this is fine-tuning again. That only happens for that particular choice of the density operator for lambda. But there clearly is causal influence from A to C here in this experiment. Indeed, from another agent's perspective who knows the coin toss, a signal can be sent from A to C. So the message of all this is supposed to be that we can conclude in both classical and quantum cases that causal influence should not be defined by signaling through an arbitrary channel. In fact, signaling is an epistemic notion. Whether Alice can signal to Bob depends on what both of them know. And you can even cook up more general examples where it depends on what Alice knows about what Bob knows, and so on. You can have an example where Alice describes the evolution by a non-signaling channel, but she knows that Bob has more information than she does, and she knows that he'll describe it by a signaling channel and can successfully send a signal to him that way. So I ask the question, in a quantum universe, what's a good notion of causal influence that's distinct from signaling through a general channel? And I argue as follows, that although fine-tuned unobserved systems can result in the absence of apparent signaling, causal influence can be defined once all relevant systems are included in the description. So that means considering that lambda so that it's not hidden anymore, let's say. And this means that we're now dealing with a closed system. And at least in standard quantum theory, closed systems evolve unitarily. So we'll be defining causal influence in terms of unitaries. So let's do that. That brings me to the next part of the talk. Causal influence in unitary transformations. First, just a bit of notation. I'm going to frequently be making use of Choi-Jamelkowski operators to represent channels. So if we consider some quantum channel, a CP map, a trace-preserving CP map, that is, with input A and output B, if the CP map is E, then we'll have the output state rho V is E acting on rho A. Let the Choi-Jamelkowski isomorphic operator begin by this expression here, and I'll write it, as you can see, as rho of B given A. So that's the Choi-Jamelkowski operator for a channel with input A and output B. And I'm choosing some particular conventions here, which I like. They're nice because this way, that operator rho is a positive operator. And also when you do things, this A star is the dual Hilbert space of A, you see, and when you do things this way, the definition of that rho is independent of the choice of basis that appears in that statement. Good. All right, and now let's talk about causal influence in a unitary transformation. Suppose we have a generic bipartite unitary U with inputs A, B, and outputs C, D. We'll say that A does not influence D if the following holds. If I consider a product input on A and B, then for all inputs rho B, the marginal of the output at rho D is independent of the input rho A. And it's important that I'm saying for all inputs rho B. So this is not a matter of fine-tuning for some particular input at B. The assertion is being made for all inputs at rho B. And there's an equivalent statement in terms of the Choi-Jamelkowski operator for that bipartite unitary U. And there's a whole bunch of other ways, actually, of making this definition, which are all equivalent. And then I'll make use of this sort of double arrow symbol. So if A does influence D, we'll write A with a double arrow into D like that. And if A does not influence D, a crossed out arrow like that. All right. Now, from this notion of causal influence, we can write down what I'm calling in this talk the Uber theorem. And I call it this because really this theorem underlies most of the rest of what I'm going to say. A lot of the other things I'm going to say will be almost immediate consequences of this theorem or consequences in some way with a bit more work. So let's consider a multipartite unitary with inputs A1 up to 8K and outputs B1 to Bn. Let me write PA subscript I for a set of the inputs that I'll call the parents of output Bi. That is those inputs Aj such that Aj does influence Bi according to the previous definition in this unitary U. So I'll call that the parental set for Bi. And then something nice happens, which is the Choi-Jamelkowski operator for this unitary decomposes in a nice way. You can write it as a product of terms where each term is of the form of a channel from the parents of Bi into Bi. And furthermore, in that product, all the terms commute. So it doesn't matter which order I write them. And a little convention applied throughout. If I'm taking a product of operators that appear to act on different Hilbert spaces, the idea is to sort of pad them with identities to make that product well-defined. Okay. So immediately, I'm going to show you a couple of nice things that follow already from this, this theorem. Oh, by the way, I'm not quite sure how to attribute this theorem. I haven't seen it quite stated quite like this in any papers except my own. But on the other hand, I don't suppose it would be much of a surprise to people who've worked in certain areas of sort of algebraic quantum field theory or quantum cellular automata or things like that. Okay, so two consequences of this, as I was promising. The first, I've got to think of a good name for this, but for now I'm calling it causal atomicity. It follows from that theorem that in a general multipartite unitary U, if AI does not influence Bj and not Bk either, then AI doesn't influence the joint system consisting of Bj, Bk. So in particular, an agent stationed at AI can't send signals to another agent, even if that other agent is doing joint measurements on Bj, Bk. And we saw earlier how this actually fails for generic classical channels. But it holds for multipartite unitaries. It also holds completely trivially for classical functions. It's not true for classical stochastic maps or quantum CP maps. But something nice follows, which is that the causal structure of a unitary can be completely specified by those parental sets, PAI, the subset of the inputs that influence each output, BI. Or equivalently, you can completely specify it by drawing arrows from inputs to outputs. So from each input, I draw arrows to all the outputs that it can influence. And you see the point here, for that to be a complete description, you needed that causal atomicity thing. Otherwise, it could happen that, let's say, A1 does not influence B3 and does not influence B4. So you wouldn't draw arrows. But then if it doesn't, if it can influence the pair B3, B4, you somehow haven't indicated that in your picture. You have to draw a much more complicated picture with subsets of outputs appearing. But because of this, this consequence, this causal atomicity, we can draw the causal structure very simply just with arrows from inputs to outputs. And here's another consequence of that Uber theorem. Causal reversibility. Suppose I consider a multipartite U, inputs A1 to AK, outputs B1 to Bn. It'll have some causal structure, which, as I argued, you can draw with arrows from inputs to outputs. Well, to get the causal structure of U minus 1, the inverse unitary, you just flip the arrows. Oh dear, I see I've drawn a silly picture because I've sort of flipped A's and B's on one side and on the other side and the arrows. Anyway, if you look at the top part of the slide and consider U minus 1 with inputs B1 to Bn and outputs A1 to AK, and to get its causal structure, you just flip all those arrows. And in case you're thinking this is somehow obvious, note that it's stronger than the mere claim that unitaries are reversible transformations. In fact, it's not even true for classical reversible functions. And the classical CNOT provides a straightforward counterexample. So it's something non-trivial. Okay. Now, so far, I've just been talking about a unitary transformation U, and I suppose we might have been thinking of it as representing evolution over a single time step with input systems at T1 and output systems at T2 or something like that. What about a unitary process over multiple time steps? It might look something like this. I've got some original inputs, lambda 1 to lambda k, a bunch of unitaries, and some outputs, mu1 to mun. There's no assumption here that U1 actually acts on all of those different systems. It could be that it only acts on lambda 1 and lambda 2 and is identity on the rest. So I'm just drawing it all the way across so that we're being completely general here. But if I drew each of those U's as acting only on a subset of the systems, we'd have something looking more like a quantum circuit with an actual structure to it. But let's be general and draw it this way. And here's what we're going to do. We break some of the wires at points that we have a particular interest in. And I've labeled them A, B, C, and D, breaks in those wires. Now here's the idea. Each break I'm going to refer to as a quantum node, and that is a locus at which we consider an additional possible evolution of the system. So if you want to bring agents into it, for example, it could be that an agent can intervene at node A, for example, and do some measurement or whatever on the system at that point. A node is associated with two Hilbert spaces, for example, HA in and HA out. The additional evolution, for example, the agent's instrument is in general a quantum instrument from the in space to the out. And this whole thing then defines a unitary supermap or quantum code. It's a supermap because you plug in maps at A, B, C, and D, and it returns an overall map from the inputs to the outputs. And I'm now going to define causal structure for this thing based on what we've already done. The idea is that we simply bend the wires. So you can see that if you look at what's happened at the A node, the A out wire has come all the way down to the bottom, and the A in wire has gone all the way up to the top. And the reason we've done that is that that whole picture now is actually completely equivalent to just some one big multipartite unitary transformation. We can call it V. And the inputs to V are the outs of A, B, C, D, and the lambdas, which I've now relabeled slightly so that they've got out written on them as well. And the outputs of V are the ins from the nodes, because we bent them up to the top. So A, B, C, D in, and mus, which I've also decorated with in. And now we're going to define causal relations between the different nodes of this process. We'll say that node X, where X is one of A, B, C, D, or maybe a lambda I, is a direct cause of node Y, where Y is A, B, C, D, or maybe one of the mu J. If and only if X out causally influences Y in that big unitary V, according to the definition that we had near the start. And it follows, as I discussed, from the causal atomicity that these causal relations can be represented by a directed acyclic graph. So it might, for example, look like that one. And it follows from the Uber theorem that the operator sigma representing the supermap, and I won't have time to go too much into the sort of formalism of supermaps. So for those who know it, at least, I'll say this bit quickly. The operator representing the supermap can be written as a product of commuting channels, where PAI superscript G now refers to the parents of node Xi in that DAG. And again, all these channels commute pairwise. Something else follows from stuff I said earlier, which is that it follows from causal symmetry, that the causal structure of the inverse process, reading top to bottom and going from mus to lambdas, is simply given by flipping the arrows. And I'm not going to go into the framework of quantum causal models too much, but briefly, a quantum causal model is then a set of nodes, with some of them, the sources, having just an output Hilbert space, some of them, the sinks, the final outputs, having just an input Hilbert space, and the rest having both in and out Hilbert spaces. And it's then also specified by some DAG over the nodes, with no arrows into sources and no arrows out of sinks. And some supermap sigma, which is written as a product of commuting terms, as we were saying. And this sort of matches quite closely the definition of a classical causal model that we had at the beginning. It's just that the nodes there were classical random variables rather than these quantum nodes. And the result says that a quantum causal model can always be obtained from a unitary process, possibly with some marginalizing over local noise sources. The framework of classical causal models is recovered as a special case when all the channels are diagonal with respect to a product basis. And many of the central results of classical causal modeling, such as the D-separation theorem, for those who know what I'm on about, have quantum analogs. Any asymmetry comes not from the causal relations themselves, because as we saw, there's this notion of causal symmetry there, but rather from epistemic aspects, such as an agent assigning a product state over sources, because that agent takes them to be independent or something like that. Right, how long? Yes, I'll do this. The commutation of the operators in the Huber theorem, or in that expression for the process sigma in a quantum causal model, induces tensor factor and direct sum decompositions of the Hilbert spaces in interesting and intricate ways. And it's really in those tensor factor and direct sum decompositions that I think we find the heart of quantum causal influence and the structure of causal relations in quantum theory. So let's just see a little bit of that. Simple thing again, suppose I have a bipartite unitary with inputs A1, A2 and outputs B1, B2. And suppose that A1 does not influence B2 and A2 does not influence B1. Well, then it's immediate from the Huber theorem that this unitary factorizes into separate unitaries V and W, and we can draw it this way. And that's nice because in the new picture now, we actually see that A1 doesn't influence B2 and A2 not B1. Let's do another example. This is a tripartite unitary now. Suppose A1 does not influence B3 and A3 not B1. Well, ask a similar question. Can the causal structure be made evident by decomposing U into a circuit? This in such a way that there's no path in the circuit from A1 to B3. And there's no path from A3 to B1. So you can actually see in the picture that A3 doesn't influence B1. Well, if there were such a circuit, it would have to look like this one here. That's the topology it would have to have. And the answer is no. Not in general. It's not true that any such tripartite unitary can be decomposed that way. But something else is true. It can be decomposed using a slightly extended form of circuit diagram that I've written here. So you'll see that it's got a similar shape, but some of my wires have got an index I on them now. And a couple of my boxes have got a VI and a WI in them as well. So the interpretation of this is best given by considering that slice across some of the wires, the red dotted line there. So that slice represents a particular Hilbert space. And it represents the Hilbert space HA1, tensor, something in big brackets there. And that something is a direct sum over different values of I of terms where each of those terms separately factors into two bits that we can call HA2I left and HA2I right, in such a way that that entire sum is isomorphic to the Hilbert space HA2. And then finally, the other wire, which corresponds to tensor with HA3 at the end. And the box with VI in it is actually a unitary transformation V acting on both of the A1 and A2 systems, but it has a block diagonal form with respect to that subspace decomposition, with VI appearing in each of the blocks. That's what those are. And also, each VI only acts non-trivially on HA2I left in that block and is identity on HA2I right. And a theorem says that any U with that causal structure at the top of the slide there can be decomposed in this way. And this idea generalizes. We managed to achieve the same sort of claim for quite a range of different causal structures of unitary transformations. So here's an example. We're considering a unitary transformation with 4 inputs and 4 outputs. Let's say that output B1 only depends on inputs A1, A2, A3. A4 does not influence B1. You can see that in the sort of bit of the picture on the left, in that there's a blue bit going around A1, 2, 3, but not around A4. B3 is only influenced by A3 and A4. B2 only by A1 and A3, and B4 only, in fact, by all of them. And the claim is that any unitary with that causal structure can be decomposed in this way, as you see in the diagram. There's a different one. Again, just another example, the sort of diagram you end up drawing so that you decompose these unitaries with given causal structures in a particular way. And that particular way means that if an input does not influence an output, then there's no path from the input to the output. There's all cases of unitaries done for all the different causal structures, where there are 3 inputs and 3 outputs. We did a bunch of 4-4 cases. Any unitary with 3 inputs and any number of outputs admits such a decomposition, or 3 outputs and any number of inputs. But it's an open question whether any multipartite unitary transformation with an arbitrary number of inputs and outputs admits one of these causally faithful decompositions. And I'd love to know the answer to that, either a proof or a counterexample. Haven't managed that so far. But anyway, let's carry on. The above applies whether the unitary transformation that we're decomposing is associated with evolution over 2 time steps, say just T1 for the inputs and T2 for the outputs, or whether it was obtained from a multi-step process by bending the wires, which led to that big V that I drew earlier, which represents the supermap. So, just looking at an example of this kind of line of argument, we could start with some process that looks like this. It's got 2 initial inputs, lambda 1 and 2, 2 final outputs, steps consisting of 4 unitary transformations. And I've broken 2 of the wires in different places and labeled them A and B. Those are the quantum nodes I'm interested in. Given that, we showed how to define the causal structure and how to represent it with a directed acyclic graph. We do that by first of all drawing the same picture with wires bent. Now that picture with wires bent is equivalent to the thing on the right, some unitary V with inputs and outputs as shown. We can define the causal structure of that V. That gives us our DAG for the original unitary process with nodes, lambdas and mu's and A and B. Say it's this one here, for example. There's some arrows missing, so it's not completely trivial here. Like you'll see that, oh, I don't know what to say. Like lambda 1 doesn't influence mu 1. Lambda 2 influences mu 2 indirectly through B, but there's no direct causal relation from lambda 2 to mu 2. So it's just some non-trivial DAG there. Once we've drawn that DAG, we can consider that unitary V. It's got a causal structure. And if it's one where we know how to do, remember there was an open question, if it is one where we know how to do, we can draw a causally faithful extended circuit diagram for that V that makes the causal structure evident in the paths. And for that DAG I drew, if that is the causal structure here, then V will have this form, according to a theorem. And then we can rebend the wires in order to make it look like the original process again that we started with, but now decomposed into one of these extended diagrams with indices. So you can see at the bottom there, lambda 1 and lambda 2, mu 1 and mu 2 coming out at the top, A and B as broken wires in the middle. And that entire process, if it has the causal structure I drew, can be decomposed into this extended circuit of unitaries here. Okay, I guess I've been talking for, what, 35 minutes?
Yeah, well, I think you have a total of like 6 minutes, including the question time. So,
yeah, okay, so let's do this really fast then, so that I leave time for questions. Here are these speculative interpretive remarks. Let's roll with the idea that the causal structure is ontic, meaning out there in the world, independent of agents. It could be, for example, that unitaries are ontic. It could be something a bit weaker than that. Just the causal structure of the unitary is ontic or something like that. Like I could take a unitary with a given causal structure, and if I apply just a local unitary at the top to each of its outputs, I get something with the same causal structure. The difference between those two things could be epistemic, with just the causal structure part being ontic. Or it could be something stronger, like unitaries are ontic. Suppose that in any quantum experiment in which one would normally say that a measurement device has a pointer and the pointer goes left or right each time you do the experiment, let's say the measurement device can be modeled entirely as a quantum system. We believe it is a quantum system after all. Well, here's the thought. The thought is that you can describe the entire experiment as a unitary process, which will have a given causal structure, which can therefore perhaps be represented by an extended circuit diagram that's faithful for that causal structure. And let's suppose speculatively that facts that obtain on an individual trial, like pointer went left, correspond to indices in that diagram taking definite values. So if there is this pointer in the diagram I've drawn, there'll be some index I such that pointer going left is actually I equals 0 and pointer going right is I equals 1, let's say. And there are various ways one could cache this out. I haven't gone too much further with this idea. It could form a new kind of hidden variable theory, defined by a joint distribution over index values for each unitary extended circuit we draw, where that joint distribution would presumably be constrained by the causal structure somehow. On the other hand, one could go more in the direction of something like Rovelli's relational QM, where indices take definite values, but only relative to other systems, not in an absolute sense, or even something Everett-like, where worlds are defined by the causal structure with indices and are distinguished by different values of indices. So it's more like they all happen at once. Okay, and actually I'm going to stop there so that we have a little bit of time left. Thanks.
Okay, thank you very much, Jonathan. That was really intense and nice talk. So, yeah, I'd like to open the room for questions.
I might jump in with a question. Oh, sorry. I'll let David Schmidt go.
David, yes, please.
Hi, John. Thanks. That was an exceptional talk. So I'm wondering if you can say anything about how causal structures compose when you compose unitaries. In particular, we've talked in the past about how it seems that you don't have transitivity of causal relations. And I'm wondering if you've thought about that in the time since we last talked.
I don't think I've thought about it more, but it's a good comment because it is worth saying. I don't think I have more to say than that transitivity fails. So if we had one of these pictures and if let's say A is a direct cause of B in my process, and then I compose it with another entire process. Yeah, let's say, actually, not B, let's say that some node A in my process is a direct cause of one of its outputs, mu. And I compose it with another process where mu is one of the inputs to that process. And mu might be a direct cause of some other node B in that process. It doesn't follow that A has any causal influence on B. Is that what you were getting at?
Yeah, I think so.
Which also happens classically just by thinking about functions. So it's not that it's some weird quantum thing, but it is something to sort of be wary of.
Good. Rob?
Yeah, thanks. Hi, John. Just a quick question about your theorem concerning the fact that if you take the inverse unitary, you flip the arrows in the DAG. So you mentioned that this was not true of classical reversible functions with C0, for example. Do you agree? Like, so my impression is that unitaries are not analogous to all reversible classical functions, but rather the subset that are symplectic transformations. So I would guess that your theorem ought to go through classically for symplectic transformations. Is that right?
Yes, it is right. I've been working on that actually with a student at the moment, and he's proved that thing. So I suspected that too, yeah, it's sort of work in progress, but I think I can say it's proven.
So
to give credit, by the way, everyone, it was Rob who came up with the C0 counter example for the classical case.
Okay, John. So in your talk, you made it seem like it was still a bit mysterious, but it doesn't seem mysterious now. Is that right? Or
well, I didn't want to call it mysterious. Sorry if I gave the impression it was a special feature of the quantum case as opposed to classical. It's a special feature of
physics.
Let's say Hamiltonian evolution, but be it classical or quantum.
Exactly. Yeah. Okay. Excellent. Thanks.
Thank you. Dan, did you have a quick question?
My question was naive and broad, so I think I'll let it pass this time.
Okay, fine. You can discuss later. Thanks. Thanks, Jonathan, again.